Hello everybody, welcome to the Probing Inspection Workshop correction video from the Advanced Training Week 2018. So we'll start by the inspection setup. To figure out what the inspection setup should be for your part, the first important thing to do is to locate all the datum features, which are very important features that you'll need to have accessible on your part. So we're starting here with our datum A, which is the plane at the bottom of the part. We're following on to datum B, which is a set of 9 holes on that plane. So what's important here is that we're going to locate these features, make sure that we know where they are and also what they are, because this will impact on how we're going to probe them and how we'll need our handy probe to be pointing towards them. Now, datum C is a plane on another flange on the side over here. You can see on the center view over here. We'll have our datum targets D1, D2, and the datum target E1 down there. It's important that these are accessible. We'll also see later that the rest of the features need to be accessible, but the datums are the most important ones. So you've got here D1, D2, and E1. Their X, Y, and Z positions are given to us by the 2D drawing. And lastly, datum F, which is the last surface on this flange over here. Now that we know where our most important features are, we are going to test different part setups that will allow us to have these features accessible for us to measure. Always keep in mind that when you're doing a probing inspection, you are going to touch the part and then apply pressure to it. This means that the part could move while doing so, and if targets are also put on other things like the table or the background, it's important that everything stays rigid. To do so, we will use different tools to make sure that the part doesn't move when we're probing. From different parts and different inspection tools, the challenge will be always different. In that specific case, there are a bunch of possible setup that would have been nice, but that we won't be able to achieve due to the rigidity of the setup. It's also important to keep in mind what are the controls of the datums, here for example the flatness of datum A, so that you know what you can and cannot do for inspection. This will also have an impact on the number of points that you might want to take and on how you'll have to access those features. So datum A had a flatness of 1.5, datum B is only the diameter of the 9 holes, datum C has a angularity of 3 mm to datum A and also a flatness of 0.5 mm, and then datum F has a flatness of 0.25 millimeters. After verifying all the other features of your inspection and making sure that the part setup that you decided to choose was actually a good one, you'll have to figure out a way to lock down the part into place. So over here, I'm using a setup where the part is set on its tubing, which makes it very unstable. So in that specific case, I'll be using hot glue to make sure that it stays into place. I'll be gluing down obviously the blocks, but also the part so that nothing moves while I do the inspection. At this point, we'll be looking at the other features that we can read on the 2D drawing. These will allow us to confirm that the part setup we decided was good enough. So here our item 5 is a surface profile of 6 mm on A and B. The little circle at the corner of the arrow means that we'll have to probe points all around the surface profile over here. For item 6, a pattern of 4 holes, we'll have a composite GD&T box, a true position of 2 mm with a maximum material condition on the datum C, D, and E, and a 0 mm tolerance with maximum material conditions on the C datum. So for these patterns, item 6 and the datum B, we will be using circles here instead of cylinders just to simplify our task, but just know that it could be possible to do the same thing with cylinders instead of circles. For item 7, we have another surface profile, this time of 1.5 mm on datum C with the little circle on the corner. That means we have to go all around the surface. Item 8 is a cylinder with a diameter of 32 millimeters plus 0 minus 4 millimeter, and a perpendicularity to datum F with a tolerance of 3 millimeters. Item 9 is a set of two circles that will be controlling their diameter of 10 millimeters. Item 10 is the distance in 3D measurement between these two circles. And finally, item 11 will be a surface profile of 12 millimeters on datum A and B of all the pipe surfaces that we have on our part. So now that the part is rigid into place, and that we verified on 2D drawing that all of our features are available to be probed, we'll be going on to our next step, the system preparation. The first thing that we'll be doing is we'll be choosing which probe and which probe extension we are going to use. So obviously over here we will be needed to probe some points behind the part, which means that the C-track, which you can imagine here being at the camera position, won't be seeing. So we'll make sure that we use an extension that is long enough, and we'll also be using a ball that has a diameter that will fit into the holes and also not be too small due to the roughness of the part. It's important not to choose a needlessly long extension, as the longer extensions tend to bend more under pressure than the shorter one. This additional bending will create more error in your system, and you want to avoid this as much as possible. So in that case here, I decided to use a 6mm ball probe with a 50mm extension. Always make sure that you set your extension and probe tight enough that it won't be unscrewing during the inspection. Making sure that you also don't screw them in too tight so that you would damage the thread of the holes. Once your probe is set up, you can verify that you will have access to all the features that you need to have access to. And once this is done, we'll be going on to our probe calibration. So this is a step that you've probably done a few times by now, nothing too complicated. So I'll let you go through your own. So now that our probe is set up, we'll be doing our target setup for the inspection. What's important to keep in mind when you're doing a target setup is you want to have the right number of targets. You want it to be distributed evenly in the volume, and you also want to cover the full volume that you'll be using to the inspection. So here we're going to use swivel targets in front and behind the part to make sure that we cover as much volume as possible. We'll also be using glass covered protected target at the front of the table to extend the volume a little bit more than with only the swivels. And then eventually we'll be using some extrusions behind and beside the part to make sure that we cover as much volume as possible. We do so because the handy probe itself will be higher above the part, and we want to cover as much height, width, and depth as possible. So for the same reasons that we used hot glue on the part and on the blocks, we'll be using hot glue on the extension and some of the targets to make sure that they stay put during the inspection. What's really important here is that we want to make sure that no targets move in relation to the part. We'll now be diving into the VX Inspect programming part of the workshop. So we'll open VX Inspect over here, make sure that we've got our C-track available, choose a probing and the right CAD model for the inspection. First thing that I always do when I start doing my VX Inspect programming is make sure that I enter the part and project information that I already have available so that I don't forget it as I go along the project. Once you're done entering the information, I'll start creating the datums. In that specific case, we'll be doing the datums first because we'll need them to create some more controls on the rest of the features. So I'll start with datum A, name it accordingly, make sure that all the information that I have over here is good, so the datum, the way that I'll be measuring it, and I'll also be changing the control so that it reflects what's on the 2D drawing right away. By doing this, I make sure that I'm not going to forget to go back and change the controls. It's also important to do the same thing, but to take off controls that you do not need, because things will appear in the report if you don't uncheck or change the controls. In the case of the circles over here, if I don't want to measure the X, Y, and Z position, it'll be important for me to take off X, Y, and Z and only keep the diameter that I want. You'll notice that when I'm picking up the nominal circles on the CAD model, I'm only selecting half of it. When you're selecting the nominal circles for a scanning inspection, it's important you select the whole thing so that the automatic extraction is done on the whole data. When you're probing, you'll manually be choosing where to take your point, and so nominally, whether you select one or two halves of the circle, you'll have exactly the same nominal circle created in the end. Here for the circle pattern, you'll notice I'm selecting the circles in the first place, and afterwards I'm going to click on circle pattern and then name the pattern as a datum B. I'll be right-clicking in the entity box, selecting the circles that I want for my pattern. So circle pattern 1-1, 1-2, and so on. As I'm creating the datums, I'll also be creating the alignments in which they appear. For example, here we've got the alignment AB, which is a datum reference frame. So I'll just go and select plain datum A and pattern datum B. Click on OK, and you'll see that the alignment AB will be assigned to all the previous features. That then leads me to datum C, which is also a plane that I'll be creating the same way I did for datum plane A. Now that I'm done creating datum C, I'll jump ahead and create the alignment C, D, and E. The reason for this is that the way to create datum targets in VX Inspect is through creating its alignment. So I'll select targets and entities and make sure that I use probe and unassign. Select datum plane C and then start creating the targets for D1, D2, and then E1. I do this approximately, and I'll go back afterwards, double click on the X position here, and I'll change it manually to what I have on the 2D drawing. For D1 and D2, I'll change the X and Y position, and for E1, I'll change the X and Z position. The reason for this is that you don't change the value that's on the normal axis of the target. It is decided by the position of the CAD model at the specified values that you gave for X and Y in that case. You can verify that it put the right value according to the 2D drawing by actually looking at the Z for D1, D2 and looking at the Y for E1. Last datum left is datum F, which is a plane on the last flange at the top of the 3D scene. This one is not used in a full alignment, so we won't be creating the alignment with datum F in it. We'll only create the datum itself with the controls that it holds on the 2D drawing. The next step here will be to detect the targets and start measuring the datums that we just created. This will allow us to have alignments in the software so that we can go and create every single features for the inspection and have our positions in regards to the targets. So we're detecting the targets as you usually would with a C-track, and we'll be measuring all the features that we have over here by clicking on the Measure All at the top of the VX Inspect page. So this goes into order. It'll start with our plain datum A over here that we'll be measuring on the part. As we probe them, the alignments AB and then CDE will become available, and you'll see on the 3D view that we'll have our handy probe linked and aligned onto our CAD model. So I'm measuring datum A over here. I'm taking a lot of points because there's a flatness measurement called out onto it. I'm going to go and measure every single circle for our datum B. You'll see that once my alignment AB is created, virtually speaking, my handy probe will be on the CAD model. I'll then be measuring datum plane C and datum targets D1, D2, and E1. I'll be measuring the targets once, and I'll go back and remeasure them a second time just to make sure that they're as close as possible to the center of the datum target. That will make the alignment CDE as good as possible. I'll finish by probing the datum plane F, accepting the feature. So we're done creating our datums and alignments, so we'll now make our snapshots that will showcase the measured values of their controls in our final report. We'll do this for every features as we go along in the workshop, just to make sure that we keep control of the snapshots we want to create and make sure that it's all clear and concise. So we make sure that the features are visible in the 3D view. We make sure that the position and the orientation of the view looks good. And we are going to create the annotations for every single features that we see here. So we've got every single circles for their diameters. We also have the plane of datum A for its flatness, and we're not going to make the pattern visible because the pattern itself does not have any control. So you position the annotations so that it looks good. And if you want to, you'll be able to change the size of the annotation in the panel to the left after creating the snapshot. So we created the snapshot. We're going to go in its properties. We can change the name. We can also change the alignment in which it's set up. And we can change the font size from 9 to any other value. In this specific case, you'll notice that I made a mistake by choosing alignment CDE for the snapshot of my alignment A and B. I will go back into the snapshot later on to change this when I notice it. We're going to clear the annotations for our first snapshot, hide the features, and now make the other features available, the one for datum C and datum F, and create a second snapshot for these two features. Going into its properties, you can see that I'm going to change the name again, make sure the font size is good. And it'll be fairly simple for me to go back into the snapshot of the first two items and change its alignment so that it fits the features that are into it. Like this. So at this point, the most crucial part of the probing inspection is done. Our datums are measured and our alignments are valid. So we'll be going one feature at a time through the rest of the 2D drawing to make sure that we have the right nominal features, their snapshots, ready for the report. We'll start with our surface profile item 5. If we remember correctly, due to the circle on the arrow, it'll have to cover all around the surface beside the datum A. We'll make sure that we have the right control set with a surface profile of 6 millimeters on A and B. I'm selecting the nominal surfaces over here all around the CAD model. And just like we did previously for the datums, I'll now be making the feature visible, creating an annotation, and taking a snapshot at the right view for the feature. Once this is done, I'll go back in the snapshot properties, make sure that it has the right font size, the right alignment, and the right name. So here I'll be measuring the surface item 5, taking points all around the surface as asked by the 2D drawing. I'll be doing this by making sure that the handy probe is pointing towards the surface so that the software can compensate the diameter of the sphere accordingly. I'm also making sure that I'm applying the least amount of pressure on the extension and on the sphere when I'm probing so that I get the least amount of bend on the extension. Using your second hand, as I'm doing over here, is a great way to make sure that you reduce this amount of tension on the extension. Although it's not possible for you to see this right now, always keep in mind that you want to be pointing perpendicularly to the C-track so that the targets are as flat as possible to the C-track's view. Moving on to the next feature, we'll now be doing our circle pattern item 6. The same way we did for the datum, we'll start by creating every individual circles before moving on to the pattern. We'll set the right parameters, making sure that we uncheck the controls that we do not want and change the tolerances of the features so that they fit the 2D drawing. You'll notice that even though there is a GD&T callout on the 2D drawing, we're not going to apply a GD&T on every individual circles, but we'll do this on the pattern itself. So here we're creating the pattern. I'm going to change the name, making sure the alignment is correct. We're going to add the 4 circles to the entity, and then we're going to change the GD&T box so that it fits what's on the 2D drawing. So the GD&T here is a composite true position with a 2 mm maximum material condition tolerance on the alignment CDE and a 0 mm maximum condition tolerance on the C alignment. I'll be using the predefined views here to create the snapshot for my item 6. I'll use annotation for individual circles here and also for the pattern because this time around it has measured values onto it. Same way I did for all of them, I'll also go back in its properties, change the name, make sure the alignment is good, and change the font size of my annotation so that they're more visible in the final report. Onto surface item 7, we'll be creating it the same way that we did for the previous surface item, again making sure that the controls are right, the GD&T is set correctly, and the alignment is good. A new type of feature that we haven't used yet is a cylinder feature for our item 8. Again, making sure the parameters are good, making sure that the controls are good, we'll be selecting the nominals. For the same reason as the circle, if you wanted to, you could only select half of it and it would still be good because the nominal would be okay. We're making sure that the controls on the diameter are not equal, +0, -4, and we're going to set our perpendicularity to the values asked on the 2D drawing. In this specific case, the alignment F didn't already exist, so we had to create a new one for it to appear in the choice list. Again, creating our annotation so that we have the snapshot for cylinder item 8. Keeping in mind the things that we already discussed about when probing, the pressure and the orientation of the probe, when probing something like a cylinder, we'll also want to keep in mind the distribution of the points that we're taking. Taking too many points on one side would make the whole measurement unbalanced. In this case here, we'll just make sure that we take the same amount of point at the same parts of the cylinder, making also sure that we take it as long as possible and on the right surface, not being on things like a weldment or on the side surface. Moving on to the next items, we'll actually be joining item 9 and item 10 together in the same snapshots and bits in the reports. We decided to do this because one is closely related to the other. The circles of item 9 are going to build the distance for item 10. This is a personal choice, and each and every one of you might have done this differently. So for the distance here, looking at the 2D drawing might not have made it obvious which distance we were going for, 3D, X, Y, or Z. Looking at the nominal value that we get here makes it clear that it was a 3D distance and not a Y distance that was asked. We're then going to go and create the annotations for the snapshot. Again, change the name of the snapshot and make sure that the font size of the annotation suits our liking. To finish our VX Inspect programming, we're going to go ahead and create surface item 11, making sure that we've got the right alignment, setting the right GD&T control onto it, and then selecting all of the nominal surfaces of the tubing as asked by the 2D drawing. You'll notice here that I'll be creating two snapshots for the surface item 11. The reason why I'm doing this is because I figured that there wouldn't be enough values shown in just one position, so I'm going to take multiple of them and then change their names accordingly. You could have easily used more than two if you wanted to, as the surface of the tubing is a very complex surface and multiple viewing angles would have been a good choice. So the last part of any inspection is to get the results out of the software into a report that the customer can look at. So what we've done here is we've verified that all of our features were measured. And we're going to go ahead and create a snapshot for the presentation page in VX Inspect. We're going to go and change the name and make sure that we check the Show in Front Page option in the snapshot. Once this is done, we're going to go ahead and export the report into the Excel format onto the desktop. At this point, we're as close as it gets to being done. We've got our final reports out in the open, almost ready to send. The only thing that we'll be doing is we'll be verifying the results that we got. The reason why we do this is that some errors in measurement, for example compensation, could have slipped without us noticing and would make the measured value way out of what they should be. So what we'll be doing here is we'll be looking at the measurements, making sure that they're all consistent and that they all make sense. We want to make sure that we don't send a report to the customer that has an obvious mistake that we made rather than a mistake that actually appears on the part. It's important to keep in mind that when you're doing an inspection, anything that is measurements related, for example, probing the datum or any feature at all, cannot be changed afterwards. This is slightly different than from a scanned inspection where you can go and change the selection of the triangle for the measurement. So we'll make sure that all of our probe points are good. Anything related to annotation or tolerances or GD&T callouts can be changed afterwards. And this is it. You've now achieved a final report that you can send to your customer regarding first article inspection. This was a rundown of the Advanced Training Week 2018 Probing Inspection Workshop. Thank you for listening.